Hi everybody, this is Mr. Ainsworth, and we're going to be starting here in the first section of Chapter 1. We're going to be discussing the two basic classic problems in calculus. You remember, in calculus there are two basic branches. The first branch is called differential calculus, involving what's called the derivative of a function, and the second branch is called integral calculus, which is basically the inverse operation of the derivative, called the integral or the antiderivative. And then we're going to be discussing two problems seen in calculus, one from the first branch called the tangent line problem and one from the second branch of integral calculus called the area problem. So let's start off with the tangent line problem. Okay, so the tangent line problem. Okay, what we basically want to do is we want to be able to find the slope of the tangent line at any point given a function f of x. All right, our goal in this case here is to find the slope and later on the equation of the tangent line okay, at any point P. And we'll call that point P, but P can be anywhere, given some function f of x. Okay, I always just generalize my functions by calling them f of x. So once again, we want to find the slope of the tangent line. Okay, the slope now. Find the slope of the tangent line at any point P given any function f of x. That's basically the tangent line problem. Coming from the first branch of calculus, differential calculus. Okay, and we can't use calculus methods here because we don't know calculus yet. So what we need to do is solve this problem right now and using only techniques we know from algebra and from the past. Okay, so let's do this. Let's set up a problem here. Let's get some axes here. Let me change that. Grab a better pen. Okay, so I'm going to just draw some axes so I can describe what's going on. Alright, and let's draw some kind of function. Function could be anything. So I'm just going to draw a part of a function here. Call this function f of x. This could be part of a parabola, it could be part of a cubic, it could be part of a sine function or cosine function. It could be any given function. Okay, P is somewhere on this function, so without lots of generality, let's put it here. Call that point P. And what we want to do is draw the tangent line through that point. Okay, or find the slope of the tangent line through that point using non-calculus techniques because we don't know calculus yet. So what we do know is algebra, and what we do know is that the tangent line is linear, and it's a line, and it must go through point P and only point P, and so crossing the function at only one point. So I'm going to draw the tangent line first, or at least the sketch of it. Put this in red. And it intersects, hang on, let me try that again. I didn't want to start at point P. And remember, the tangent line intersects the graph at only one point, so I'm a little bit off right here, so let me change that one more time. Try this one more time here. Okay, it intersects the graph at one point, so there is an approximation of the tangent line. There's somewhere right there. It has to go through point P and intersect the function at once. The question is, how do you get the slope of that line using non-calculus techniques? Well, what we do know is since the tangent line is linear, it requires 2 points to find the slope. So if I pick another point on the function, let's say up here, let's call it Q1. Q1 right here. We could find the slope between P and Q1 and approximate it, the slope of the tangent line, using what's called a secant line. Let me graph that. Okay, so this line right here is called PQ1, and PQ1 is is a secant line. A secant line is a line which intersects the function twice, and it goes through Q and it goes through P. Now, you notice that the slope of PQ under the secant line is pretty steep, and it's much bigger than the slope of the tangent line, which is what we want. So it'll give us approximation, but not a very good one, because it's too steep. So the question is, how do you get a better approximation of the slope of the tangent line? What do we do with Q1 here, to make it better? Okay, and the answer to that question is that, hey, why don't we just slide Q1 down closer to point P? So if we do that, let's say Q2 is down here. Make them big points so you can see better on the screen. Call that Q2. And if I graph PQ2, which is the next secant line, I have a better approximation here. There we go. Right there. So this is PQ2, and it's another secant. And you notice that the slope's not as steep as PQ1. So it's a better approximation for the tangent line in red. Still not good enough, though. So what do? Well, we get closer to P. We slide Q, and we slide it, and we want Q to get really close to P. In fact, we want to do what we love to do in calculus, is that we want to go infinitely close to P. So we slide, the basic idea, okay, is to slide Q, we'll call it Q sub I for in general, Q1, Q2, Q3, slide Qi infinitely close to P. So Qi approaches P. And so they're very, very close. They're super close. They're so close that they're indiscernible. Okay? And that will get a better and better approximation for the slope of the tangent line. It'll never become exact unless you take a limit, which we'll talk about later on, but it'll be really, really close. And that's the basic idea. All you have to do to get a really good approximation for the slope of the tangent line is to pick a point very, very close to P on either side of the function. Okay? So let's take that idea and apply it to a real example here. Call this example 1. What we want to do is given a real function now, so given, let's say f of x is equal to negative 1/2 x squared plus 8, find, we'll call this part A, find the slope of the secant line first, of the secant line through P, okay, and let's say P is 1, 7.5. That's on the function. If you substitute 1 into the function f here, you get 7.5, where f of 1 is 7.5. And Q, which is a little bit to the right of P, let's say that it's 1.5, let's say y. Okay, we'll have to figure out what the y value is in a minute. Okay, that's the first thing we need to do, find the slope of the secant line. And then after that, part B, what we'll do is we'll get a really good close approximation of the slope of the tangent line. Okay, first thing you have to do on a problem like this is graph the function. Okay, so you can see what's going on. That's what you have to do when you're learning. All right, so let's graph the function here. Let me change that color. That's not a good color. So get some axes here. Okay, and let's set up a table so that we can graph the function here. If you don't know what this that this looks like a parabola, then all you have to do is set up a table of values, and then do what you did in Algebra 1. You plot points. 0, 1, 2, 3, 4, and so on, and then use your symmetry on the parabola. I already know by looking at this function that because of the negative sign here, this parabola opens down. The fact that it's 1/2 versus 2 means that it opens up wider than normal. And the fact that we're adding 8 here, it means that it's shifted up 8. So if you know those facts, great. Okay, you remembered stuff from Algebra 2. But here we go. If you substitute 0 in, you get 0 squared is 0 times negative 1/2 is 0 plus 8 is 8. So f of 0 is 8. Substitute 1 in, you get 1 squared is 1 times negative 1/2 is negative 1/2 plus 8 is 7.5. 2 squared is 4. 4 times negative 1/2, negative 2 plus 8 is 6. And 3 squared is 9 times negative 1/2 is negative 9/2. Negative 9/2 plus 8. So negative 9/2 is negative 4.5 plus 8 is 3.5. And 4 squared is 16 times negative 1/2 is negative 8 plus 8 is 0. And then you use symmetry and you reflect these across the y-axis. So let's plot. Let's go up 8. 1. This is 2, 4, 6, 8. That's 8. Let's plot a point. And that's 2, 4, 6, 8. So there's 4 here. And let's see here. 1, 7.5 is up here. And 2, 6 here. And 4, 0. Then use symmetry. And then go ahead and graph your parabola. Okay. Now we're trying to find the secant line through P and Q. So I'm going to graph those. P is 1, 7.5. 1, 7.5. And then Q is 1.5, y. So where is that? So you're going to have to substitute 1.5 in. And 1.5 is 3/2. So I need to evaluate negative 1/2 times 3/2 squared plus 8. So it's negative 1/2 times 9/4 plus 8. That's negative 9/8 plus 8. That's negative 1 1/8 plus 8. And 8 subtract 1 is 7 minus 1/8 is 6 7/8. So 6 7/8 here. So I go right 1.5 up here, 6 7/8. There's Q. At 1.5, 6 7/8. Now my tangent or my secant line looks like this. And then there's a decent graph. This is PQ right here, and there's your secant line. Question is, what's the slope of that? Okay, and just remember, slope's simple. Just recall the definition of slope from Algebra 1 is rise over run. y2 minus y1 divided by x2 minus x1. There's your definition of slope. And all you have to do is apply it. So let's do that. So we have 7.5 minus 6 7/8 and divided by 1 minus 1.5. And that's going to be equal to 7 4/8 minus 6 7/8 is 5/8. And then divided by negative 1 and negative 1/2. That's the same as 5/8 times negative 2, which is negative 10/8 or negative 5/4. Now, just so you know here, the slope right there, and this is the slope of the secant line. Slope of PQ. This is your secant. The slope is negative 5/4. That's our approximation. But I can tell you that the exact slope of the tangent line, using calculus techniques, is negative 1. And so negative 1 1/4 is, it's pretty close to negative 1. So we're pretty close, but not exact. All right, it's close. The question is, how do you get a better estimate? So the next thing I want to do is I want to estimate the slope of the tangent line now by making Q go really, really close to P. So estimate the slope of the tangent line through P, which is 1, 7.5, and using a closer point than we originally had, and Q, so let's make it really, really close to P. Let's make the x-coordinate very, very close to 1. So 1 point, let's say 0, 0, 0, 1, let's say y. And this will give us a very close approximation. Remember, I said that the exact answer for the slope of the tangent line is -1. You don't need to know that now or know how I got that. I'll show you that later, but just keep that in the back of the mind. The exact slope, okay, exact slope of tangent line here. Okay, is equal to -1. You don't know that? Okay, just accept that. Okay, so let's see what we get here. What I want to do is show you how to substitute this into the function without, a different way, because sometimes you're going to have to evaluate points using multiple x coordinates, and the fastest way to do that on your calculator is this way. So let me show you. Let me grab my calculator here. There we go. Get your TI-83 or 84 going here. And let's turn it on. And let's clear it out. Okay, and let's clear this function here. Now, first of all, we enter the function in. Okay, so let's do that. Let's -0.5, or you can go 1 divided by 2 for 1/2, x squared plus 8. Go to zoom. Select number 6 for Z standards. That will make sure that your graph looks like mine. And you'll notice that it looks like the graph that I showed you there. Up here at 0.8 is the y-intercept there, and it's at the top vertex, and it intersects at 4 and -4 on the x-axis there, which corresponds to my graph. Over here, let me show you here. See? The x-intercepts are 4 and -4, and the y-intercept is 8. Okay, so let me get my graph back here. Now, what you want to do is go to trace mode if you want to evaluate a point. So you select y1, that's the only function we entered, and down here at the bottom are your x and y coordinates of any point on the function. I want 1.5, y. I want to know what y is when x is 1.5. Excuse me, not 1.5. Let me scroll down here. I want to know what y is when x is 1.0001. So you could input, -1/2 on your calculator times 1.001 squared and then add 8 and do it that way. Yes, you can do that. Another way to do it is using your trace mode. All you do is enter in the x value, 1.0001, hit enter, and up here on the screen where it says the y value, that's your y coordinate. And notice where it is on the graph. Okay, so y is 7.499999. Okay, so let's record that. So when we do this using trace mode, or you can just directly evaluate it on the calculator, I found that Q is 1.0001, 7.499. We'll add another 9 there. Okay, so now we want to find the slope of the tangent line using these 2 points, because now P is super close. All right, super close to P. And that's what you want. You want to be super close. I mean, 1 and 10/1000ths is very close to 1, because 1 10,000ths is small, super small. So here we go. Let's get the slope. So the slope is equal to y2 minus y1, so 7.5 minus 7.4999 divided by 1 minus 1.0001. And we do this on the calculator. Now, when you do it on the calculator, make sure that you include parentheses around the numerator and denominator, because otherwise you won't get the same value. So let's bring the calculator back. And let's go second mode, or quit, and that gets you the home screen. Let's go left parentheses, 7.5 minus 7.4999, parentheses, all right, close it off, divided by, parentheses, 1 minus 1.000, oops, go back 1, 1. There we go. End parentheses, enter, and look at that. The calculator rounds the result to -1. So, -1, which is close to exact. I mean, exact is -1, remember that. So this is very close. Yeah, I'd be happy about that. So if you want a good approximation of the slope of the tangent line, get super close to P, the point of tangency, wherever you're considering, and use your calculator, and you'll get a really good approximation. All right, and that's the tangent line. That's your first classic problem in calculus there. All right, the next one is called the area problem. This is part B now, or second part, and it's the second basic problem in calculus, and it's called the area problem. And the area problem goes like this. What we want to do, here's your basic idea or the goal, is the following here. We want to find the area, okay, under the curve, and we're going to call the curve, but it could be any curve. It can be polynomial, quadratic, any type of polynomial, any type of trig function. It could be a combination of the two. It doesn't really matter, but we're going to call it f of x in general. Okay, so find the area underneath the curve, f of x, and above the x-axis, you can find areas underneath the x-axis too, but that's a little bit more complicated, so let's just stay above the x-axis for this example. And let's do it from a to b, which are called bounds, or bounds, left and right bounds, from x equals a to x equals b, or basically from a to b. Okay, what we want to do is draw a picture of this and kind of get an idea of what we're doing. So let me get some axes here. Okay, and let's get a function here. Call this f of x. Okay, now let's say that a is here, and b is here. A and b can be anywhere on the x-axis here. These are x coordinates, obviously. And let's suppose we want to figure out the area from a to b above the x-axis and below the curve. So I'm talking about this area right here. Okay, all that area in there. Okay, what's the area beyond that? Now, in geometry, you study how to find the area of all types of polygons and, you know, basic nice shapes. Okay, but you've never done this. You've never found the area below a curve like this. So what we do is we approximate it first, and later on in integral calculus, we learn how to get the exact value. Now, what we're going to do is we're going to use rectangles to do this, and we're going to start with rectangles because it's an easy concept to deal with, and later on we could switch it to other geometrical shapes like trapezoids and other things. All right, but we're going to use rectangles. So let me actually put that in, using rectangles, because, you know, there are different ways you can do this. Okay, one thing you can do is to get an approximation is to use one rectangle, and then later on use two rectangles, and then maybe use 4, and then use maybe 8, and then 16, and see what happens. What can you do to get a better and better approximation for the area underneath the curve? So, and then you have to design your figure out how you're going to design your rectangles. You're going to be coming from the left, you're going to be coming from the right of the interval. Okay, now the interval is from a to b, and the distance from a to b is found by taking the right endpoint, subtracting the left, so that's b minus a. That's the width of your rectangle there. And your height on the left side, if we use the left side and we're coming from the left, is found by taking a, going up to the function, and moving left. And since we're going to evaluate at the function, you got to evaluate at a. We'll call that f of a. So if you're going to design your rectangles from the left, it would look like this for one rectangle, one rectangle only. Let me get a red pen here. So you go start at a, the left side of your interval, go up to the function, top it off, and come back down. Now you notice that there's some error involved right there. All right, this is going to be a low estimate here. All right, because we didn't include the area above the rectangle there, but underneath the function. So this would be a low estimate. So what can we do to get a better estimate? Well, we can perhaps come in from the right instead of the left. So let me switch colors on that. Suppose I come in from the right instead of left. We'll see what kind of estimate we get there. So taking a look at the interval from a to b, I come in from the right side, I go up to the function. Wherever I meet the function, I top off the rectangle. I come back down. Now notice the area in the green rectangle here coming in from the right side of the interval gives me an overestimate. So all this area right here, all this is error, and it gives you a high estimate. So if you come in from the left, it's different than coming in from the right. You have one estimate that's different than the other. So pay particular attention to your directions when you do your homework. Are you designing rectangles from the left or from the right, and how many are you using? In this first diagram, I use one. Now, you don't have to use one. If you want to get a better representation or a better approximation, you should use more rectangles. So let me draw the same picture, but over here, and show you what I'm talking about. And let me draw the function again. From A to B. That's not exactly the function. Let me change that a little bit. More like that. Okay, so there's basically the same function. We're coming in from A to B. Okay, and so there's the same width of the interval. Now if I use two rectangles, I'm going to divide the distance up into two equal parts. So I take this distance, b minus a. Okay, that's the length of the interval here, and I divide it, and then I want to take half of that. So my width of the rectangle from here to here should be b minus a divided by 2. Now if I was going to design this or approximate the area with two rectangles, coming from the left, I would start on the left side of the subinterval. Okay, this is called a subinterval. And I come in from the left, I go up to the function and top it off. I come back down. Then the next subinterval on the right, you come in from the left, you go up to the function, top it off, come in, and then come down. So wherever it meets the function, top it off and come back down. Now you notice this looks just like the previous one in red. So it's going to give us a low estimate. Alright. So the question is, what can you do to improve it? Well, you could come in, you could do four rectangles. Okay, and if you did 4 rectangles, it would look like this. You come in from the left, and then from the left again, then from the left again, and then from the left again. And you notice that the error here and here has gotten smaller. Okay, so if you increase the number of rectangles, the error gets smaller. And if you increase them to 10 rectangles all the way up to 1,000 or 100,000 rectangles, the width of each rectangle decreases as you increase the number of rectangles, and the error gets smaller and smaller, and pretty soon you approach the exact value. And that's what we want to do in calculus. Is we want to learn how to sum up an infinite number of rectangles that are infinitely thin in width. Pretty cool. All right, so let's take an actual example here, and then go for it. All right, and let's use the previous example, the previous function here. Let's given f of x is equal to negative 1/2 x squared plus 8. Let's say given this. Let me write the word given. Given that function, okay, find the area underneath the curve, area under the curve, and above the x-axis. Let's say from x equals 0, oops, no comma there, to x equals 4. Okay, using, let's say, 4 rectangles. Okay, coming from the left. Okay. So, we need to figure out the length. We need to graph the function again. We need to figure out the width of the rectangle given the fact that we're going to use 4. And then we need to draw the rectangles and calculate their widths and their heights. Find the area of each rectangle, and then add up the areas. So the first thing we do is we graph the function. We already did this before, so this should go fast. So I'm not going to explain it again. I'm just going to do it. And it goes again. You go up to the top here and you get your table of values, which is right here. So let's grab them. Okay, and let's copy that. And let's bring them down here. Let's use them. You do this on your own. Whoops, come on. Okay, those are our points. We already did that. And so let's go ahead and plot again. 0, 8, 2, 4, 6, 8. Plot a point. 1, 7.5, and then 2, 6, 3, 3.5, 4, 0. Reflect on the other side, which we don't need to do, but I'm going to do it anyways. Okay, there's your f of x. There's your function. And we want to approximate the area underneath the curve from the x-axis from 0 to 4. So 0 is here, and 4 is right here. And we want to use 4 rectangles coming from the left. So the first thing we do is we calculate the interval. Right there, the interval is 4. Okay, it's found by taking 4 minus 0, which obviously 4. And remember, the width of rectangles is always found by taking b minus a divided by how many rectangles you have, and this is the number of rectangles. So for us, this is going to be 4 minus 0 divided by 4, and that's 1. That's equal to the width. Okay? So now we're going to come from the left. Right there. Okay, so I'm going to go up to, on the left side, start on the left side, go up to the function, top it off, come down. There's my first rectangle right here. And at 1, between 1 and 2 is my next subinterval. I go up from 1 to meet the function, I top it off, and come back down. Then at 2, go up to the function, top it off, come back down. Then at 3, go up to the function, top it off, and come back down. So you can see right off the bat that there's a little error. There's actually quite a bit of error in all those little regions that are in blue. Okay? And these are the errors. This is actually a good example of a high estimate because I've got over, all these areas are going to be over and above the actual function here. What I want is the area underneath the curve, the area in yellow only. That's going to be lower than what I'm going to get. Okay? I'll show you the exact area in just a minute. So what we want to do is find the areas of these rectangles. And for each area, you take length and multiply width. So we'll call this one's A1, okay, and then A2, and then A3, and then A4 here. We want to calculate the area, so the total area here is going to be found by taking A1, add it to A2, and add it to A3, and add it to A4. Okay? Now it's always width times height. Or length times width, it really doesn't matter. The width of each one is 1. So all we have to do is take 1 times the height. Which is basically all we have to do is add up these function values. Okay? So the height of the first rectangle is obviously at 8, because f of 0 is 8. So this is your y1 right here at 8. And then the height of the second one right here is at 7.5. So it's going to be 1 times 7.5. So 1 times 8 plus 1 times 7.5 plus an A3, it's going to be 1 times this height right here. And that's f of 2. And f of 2 we found to be 6. And then f of 3 we found to be 3.5. Okay? So plus 1 times 6 plus 1 times 3.5. I'm just putting the ones in there so you know that I'm taking width times height on each one. So 8 plus 7.5 plus 6 plus 3.5. Let me see. So adding up the whole numbers, we've got 8 and 6 is 14, 7 and 3 is 10. That's 24 plus 1 more, 25. So 25 square units. And just so you know here, Let's see. Let's calculate the actual here. In calculus, the area would be found by finding the integral from 0 to 4 of the function negative 1/2 x squared plus 8. Okay, and so that'd be found by taking negative 1/2 x cubed times a third, or divided by 3, either one, alright, plus 8x here, evaluate it from 0 to 4. And I know you guys don't understand this because we're not in the second branch of calculus yet, but I just took an antiderivative or an integral, and I'm now going to evaluate it 4, the function at 4, then subtract that to 0, which is going to be 0. So this is going to be negative 1/6 times 4 cubed plus 8 times 4. Okay, and that's going to be negative 64/6 plus 32. And that's going to be negative 10 2/3 plus 32. So that's 32 minus 10 2/3. So that's 22 minus 2. It's 21 1/3. So 21 1/3. And there's square units, and there's your exact. Okay, so you notice our approximation is 25. It's bigger than our exact of 21 1/3, and the reason why is because look at these blue areas right up here. The blue areas are overestimates, so we expected a bigger answer when we started in the beginning, and we did. We got 25 versus 21 1/3. Okay. All right. So all you have to do is figure out the width of the rectangles by figuring out the length of the interval, which is 4 in this case, divided by how many rectangles you have, which is 4. So the width is 1. And then if you come in from the left, you go up to the function and then top it off. And then the next interval on the left, go up to the function, top it off. If you're coming in from the right, it look totally different. It would look way different. Let's see if I can grab this here so I don't. Whoops, let me try that again. Let me discuss that just briefly here. Okay, if you came in from the right, let's say, let me switch to, let's say, green here. The first you wouldn't have a rectangle on the first one here. Whoops, what happened there? Come on. Don't know what happened. Let me try that again. There we go. Okay, and let me put in a line here, the x-axis, so I can see it better. There we go. So ignore this. If you come in from the right, you're not going to have a rectangle on the first interval. What in the world? Why does it keep happening? So, and then you come in from the right on the second subinterval here. It's going to be a low estimate. And then from the right, a low estimate. And then from the right, another low estimate. So the ones in green are you're going to have only 3 rectangles as opposed to 4. And they're going to be low estimates because notice that the yellow areas have not been accounted for. So this gives you a low estimate coming in from the right. So it matters. Okay, that's what I'm saying. It matters on how many rectangles you use, and it matters whether you come in from the left or from the right. And it also matters on the slope of the curve, which determines the type of error or the type of estimate that you're going to get. Okay, so give this a shot. Try your homework problems, 7, 8, 9, and 10. And then you can ask me questions tomorrow. See you then.